Course 3, Industrial Processing, Operational and Financial Management in Food Processing, Operational Efficiency and Cost Management. Before we enter the technical content, this module focuses on operational and financial management in food processing, emphasizing the relationship between operational efficiency, cost control, and financial sustainability. Food processing enterprises operate under strict regulatory requirements, high resource use, and narrow margins, making efficiency and sound financial decision-making essential for competitiveness and resilience. The module introduces key concepts related to food production workflows, common sources of inefficiency, and practical tools for analyzing and improving operations. It also addresses startup finance in the food sector, exploring financing needs, funding options, and basic financial planning. Particular attention is given to economic flexibility and financial risk management, highlighting how efficient operations and waste reduction contribute to profitability, liquidity, and business resilience. Applied examples and practical exercises support learners in linking operational decisions with financial outcomes, promoting informed, data-driven management in food processing startups and small enterprises. In Submodule 1, we will describe common food production workflows and identify operational inefficiencies within food processing environments. During this session, we will explore how food processing plants convert raw materials into finished products and how inefficiencies can emerge throughout the production chain. These inefficiencies affect cost structures, food waste, quality performance, and overall competitiveness. Understanding these dynamics is essential for anyone involved in food processing operations, plant management, or entrepreneurial decision-making in the agri-food sector. Operational efficiency is particularly important in the food sector for several reasons. First, food products are highly perishable, which means that delays, waiting time, and unplanned stoppages can result in spoilage or reduced shelf life, making inefficiencies very costly. Second, food processing is subject to strict regulatory and hygiene requirements that impose traceability, quality, and safety controls. These constraints must be met consistently while production continues. Third, profit margins in many food categories are thin, especially for commodity products, meaning that waste, rework, and variability directly erode profitability. Finally, demand volatility requires responsiveness, flexibility, and short lead times. For these reasons, operational efficiency enables food businesses to meet regulatory, quality, and market expectations while managing resources effectively. Operational efficiency refers to the ability of a food processing plant to transform raw materials into finished products using the minimum amount of time, labor, energy, and materials necessary. However, efficiency must be achieved without compromising quality standards, food safety requirements, or regulatory obligations. Efficient operations minimize waste, reduce process variability, and improve production performance. This means that efficiency in food processing is not simply about producing faster, it is about producing reliably, safely, and with lower resource consumption. Operational efficiency is more than an engineering or technical concern. It is also a strategic and entrepreneurial capability. When food processing businesses design and manage efficient processes, they are able to compete more effectively on cost, reliability, and sustainability. Cost advantages arise from reduced waste, lower resource consumption, and improved margins. Reliability is strengthened through consistent production performance, predictable throughput, and stable lead times. Sustainability benefits come from reductions in food waste, energy usage, and water consumption. These combined advantages strengthen competitive positioning in modern food supply chains, where buyers and regulators increasingly expect efficient and sustainable operations. Food companies increasingly adopt lean manufacturing and continuous improvement approaches to enhance productivity and reduce waste. Although lean methodologies originate from discrete manufacturing, scientific studies show that adapted lean tools can generate significant operational improvements in food processing environments. These improvements include reduced food losses and waste, shorter changeover and setup times, lower hygiene-related downtime, reduced process variability, and improved responsiveness to fluctuations in demand. It is important that lean tools are aligned with regulatory and food safety constraints in order to be effective in food processing environments. Lean manufacturing provides several tools that have proven useful in food processing environments. The first is value stream mapping, or VSM, which is used to visualize the full flow of materials and information within a production system. VSM helps identify bottlenecks, unnecessary waiting time, excess work in process, and points where food losses occur. The second tool is 5S and workplace organization. In food environments, 5S supports hygiene compliance, reduces unnecessary motion, and facilitates cleaning and sanitation routines. The third tool is standardized work, which is essential for ensuring batch reproducibility and reducing variability in operations such as portioning, filling, cutting, or mixing. Together, these tools help minimize non-value-added activities and improve operational stability in food processing plants. Two additional lean tools are particularly relevant in food processing. Total Productive Maintenance, or TPM, focuses on minimizing equipment downtime and improving line stability in critical thermal and mechanical equipment such as ovens, cookers, fillers, and refrigeration units. The second tool is SEMED, or Single Minute Exchange of Die, which shortens changeover times in multi-product environments. Shorter changeovers reduce startup waste and increase available production time. Scientific literature shows that when adapted properly, lean practices contribute not only to productivity gains, but also to the strategic objectives of minimizing food losses, strengthening quality assurance, and improving the economic sustainability of food processing businesses. Although food processing varies widely by product category, most food manufacturing plants share a similar workflow. This workflow includes raw material reception and inspection, storage and internal logistics, pre-processing, transformation or processing, packaging and labeling, and finished goods storage and dispatch. Understanding this typical workflow is important because inefficiencies can emerge in any of these stages. By understanding how these stages connect and where variability or delays occur, it becomes easier to identify operational inefficiencies and to target improvement initiatives. In the first stage of a food production workflow, raw materials arrive from suppliers and are unloaded at the receiving dock. Initial checks are carried out to verify quantity, temperature, transport conditions, and visible damage. Quality and safety inspections may follow, including sampling and laboratory analysis to verify compliance with specifications and food safety requirements. Traceability data are also recorded at this stage. Common inefficiencies in this phase include long unloading and inspection times, poor scheduling of deliveries, and inadequate sampling procedures that delay release to production. These delays may force plants to operate with higher safety stocks, increasing storage costs and spoilage risk. The second stage of the workflow is storage and internal logistics. Raw materials and intermediate products are stored under controlled temperature and humidity conditions. Inventory management typically follows FIFO or FIFO principles to minimize expiry and quality degradation. Internal transport may involve forklifts, conveyors, pipelines, or automated guided vehicles. Inefficiencies at this stage often stem from poor layout design, which causes long transport distances, bottlenecks in cold storage areas, lack of standardized handling procedures, and inaccurate inventory records. These issues contribute to unnecessary motion, waiting, food losses, and higher energy consumption. The third stage in the workflow is pre-processing, where raw materials are prepared for transformation. This stage may involve washing, peeling, trimming, cutting, sorting, grating, thawing, or preheating, as well as mixing and dosing of ingredients. A significant share of food loss and waste can occur at this stage due to trimming, overpeeling, cuts that fall out of specification, or poor control of washing and thawing conditions. International organizations such as the FAO highlight processing and manufacturing as critical hotspots for food loss and waste in many supply chains. The fourth stage of the production workflow is transformation or processing. This is where prepared raw materials are converted into finished or semi-finished goods using a range of operations. These may include thermal processing such as cooking, baking, pasteurization, or sterilization, mechanical processing such as mixing, grinding, emulsification, or forming, biochemical processes such as fermentation, or preservation steps such as concentration, drying, or freezing. At this stage, inefficiencies can arise from equipment downtime due to breakdowns or cleaning, capacity imbalances between upstream and downstream machinery that create bottlenecks, and issues such as spillage, overfilling, or off-spec products that must be reworked or discarded. Poor process control, including fluctuations in temperature or inconsistent mixing, can also lead to variability and defects. Case studies in food processing show that applying lean tools and total productive maintenance can increase overall equipment effectiveness and throughput while reducing waste. The fifth stage of the workflow is packaging and labeling. After processing, products are filled and sealed into appropriate containers such as bottles, cans, trays, or pouches. Some packaging processes include gas flushing to extend shelf life. Labeling and coding are then applied to provide batch and expiry information for traceability. Finally, products are packed into secondary and tertiary packaging such as cartons, cases, and pallets. Common inefficiencies at this stage include long changeover times between formats or product variations, mislabeling or coding errors, packaging material defects, and unplanned stoppages on high-speed packaging lines. Studies using value stream mapping in food and packaging operations show that long setup times and uneven line balancing are major contributors to waiting time and overproduction. The final stage of the workflow is finished goods storage and dispatch. At this stage, pallets are stored in finished goods warehouses, which may require refrigeration or freezing. Orders are picked and consolidated before being loaded onto trucks for distribution. Inefficiencies at this stage often include poor coordination between production planning and logistics, leading to double handling and excessive storage times. Plants may also encounter incomplete loads or urgent shipments that increase logistics costs. These inefficiencies are significant because food products are perishable and delays can reduce shelf life, increase waste, or negatively affect service levels. In lean manufacturing, 8 types of waste are traditionally distinguished: transport, inventory, motion, waiting, overproduction, overprocessing, defects or rework, and underutilized people. In food processing environments, these waste categories interact with sector-specific characteristics such as food safety requirements, perishability, and regulatory compliance. This interaction creates unique forms of inefficiency that may not appear in other industries. For example, waiting time in food processing can translate into direct product spoilage, and rework may carry both material and food safety implications. A major category of inefficiency in food processing is food loss and waste. Processing-related food loss and waste includes trimming and cutting losses that exceed what is technologically necessary, spillage and leakage during transfer or filling, off-specification products that require downgrade, rework, or disposal, and expired inventory due to poor planning or long storage. Food loss and waste carry financial implications due to the cost of raw materials, labor inputs, energy consumption, packaging inputs, and disposal fees. Processing is a significant hotspot for food loss and waste in product categories such as fruits and vegetables, meat and poultry, and dairy products, which are highly perishable. Economic analyses show that targeted interventions to reduce food waste often generate positive returns because avoided disposal fees and recovered yield outweigh the costs of improvement. Another important category of inefficiency in food processing relates to equipment performance. Equipment inefficiencies include breakdowns and unplanned downtime, micro stoppages and speed losses such as minor jams or adjustments, and reduced capacity utilization due to frequent changeovers or cleaning. These losses are often measured using overall equipment effectiveness, or OEE, which multiplies availability, performance, and quality to produce a single indicator of equipment performance. Case studies in food processing plants report OEE improvements of 20 to 50% after focused interventions in maintenance, setup reduction, and standardized work, with strong positive effects on unit costs and service levels. In addition to food losses and equipment-related inefficiencies, process and layout design issues also contribute significantly to inefficiency in food processing operations. Unbalanced lines can create bottlenecks and work-in-process accumulation. Poor layout design can lead to long internal transport routes. Cross-flows of materials and people may complicate hygiene zoning and increase contamination risk. Planning and scheduling inefficiencies can arise when production schedules change frequently, leading to partial batches and unnecessary changeovers. Long changeover times reduce available production time and may generate off-spec products during startup. In multi-product environments, suboptimal sequencing can increase cleaning and sanitizing requirements. Studies combining value stream mapping and simulation in food SMEs show that redesigning layouts and sequencing can reduce lead time, work in process, and handling costs. Another category of inefficiency in food processing relates to utilities, including energy, water, and other support systems. Inefficiencies may include overheating or overcooling, running equipment while idle, excessive water usage in washing and cleaning operations, compressed air leaks, and inefficient steam systems. Operational and waste management studies in the food and beverage sector emphasize that better measurement and control of utilities can reduce costs and environmental impact simultaneously. Reducing utility consumption supports both financial and sustainability performance, which are increasingly important dimensions in food supply chains. Several analytical tools are available to help identify inefficiencies in food processing workflows. Value stream mapping documents the current and future states of material and information flows and helps identify bottlenecks and non-value-added activities. Overall, equipment effectiveness measures performance by combining availability, performance, and quality into a single indicator. Yield, waste, and rework indicators link production efficiency directly to material costs, particularly in processes where small percentage improvements generate substantial savings. Cost structure analysis helps identify cost drivers related to materials, direct labor, manufacturing overhead, and waste disposal. Additional tools such as statistical process control, HACCP, and digital traceability systems support monitoring, safety, and optimization. Together, these tools enable data-driven decision-making in food processing environments. Scientific case studies demonstrate the practical value of structured analysis tools and targeted improvement projects in food processing environments. Studies report that using value stream mapping to redesign layouts and flows in small food plants reduces non-value-added time, work in process, and operating costs, while increasing throughput and service level. A separate case study in a food processing plant showed that focusing on setup time reduction, standardized cleaning, and preventive maintenance significantly increased overall equipment effectiveness, effectively doubling the useful output of a key line without major capital investment. Food loss and waste reduction measures also recover yield and reduce disposal costs while contributing to sustainability goals and regulatory compliance. Operational efficiency has important entrepreneurial implications. Understanding production workflows allows for more realistic business planning in terms of capacity, staffing, and investment needs. Identifying inefficiencies provides a basis for continuous improvement and competitive cost structures. Using analytical tools supports data-driven decision-making rather than intuition. Reducing food losses and waste is both a cost management strategy and a key element of sustainable and resilient business models. Thank you.